All right, everybody. So we have looked before at identifying function families from a graph. Today, we're going to look at identifying a couple function families from a table. So I have an I can statement for you. It says I can, given a table of values, determine the function family it represents. So again, rather than seeing a picture of a function, you are going to be looking at some X and Y values in a table. All right, so the function families that we are going to be able to identify, we are going to look at 4 of them. We are going to look at exponential, quadratic, linear, and non-functions or relations. Those are the 4 options that you're going to have when you're looking at a table and deciding which function family it is part of. So again, those are exponential, quadratic, linear, and non-function or relation. All right, so let's get to it. We have basically 3 options. Now, we have already previously looked at non-functions or relations. We know that that something is a relation if we have repeating X values. So that's one thing we've already tackled. However, we have not looked at how to identify linear, quadratic, or exponential functions from a table. So here are our rules. Linear functions will have a common difference. And we looked at this with our learning target 6.2.2, where you were given a sequence and you had to find a common difference in the sequence. So if there exists a common difference, you are looking at a linear function. If there exists a common, now this one's a little bit funky, a common second difference, and I'll show you an example of that, that means that we have a quadratic function. And if there is a common ratio, so again, that means if you can divide and get the same number between all of our values, then you're looking at an exponential function. So I'll pause for one moment in case you need to soak that in, and then we'll go through some examples. All right, example 1, we're going to look at a linear function here. So we have our table of values. I got some X's and I got some Y's. Now for X's, all you want to do is make sure that we are counting 1 every time. All right, in this case, we are -1 to 0, 0 to 1, 1 to 2, 2 to 3. So that is good. Now we're really going to evaluate those Y values. Those are going to be the telltale to let us know what type of function we're looking at. So if I am looking at a linear function, I'm going to, as I said, we're looking for a common difference. So I am going to subtract the previous Y value to determine if I get the same number every time. So 11 minus 5, that's going to give us 6. 17 minus 11, that's going to give us 6. 23 minus 17, again, that will give us 6. And our very last set of terms, we will also get 6. Once I see that we have the same number all the way through all of my Y values, I can identify for sure that this is a linear function. I'll pause for just 1 second in case you were writing this down. All right, so I'm going to move on to our second example, and this one is a little bit new to us. We haven't seen a second difference. So quadratics, like I said, we have a common second difference. So that means, let me make a little note of that, second difference. So that means basically we're going to do the same thing we just did with our linear function, but we're going to do it 2 times. So again, like always, I'm going to make sure that I'm only counting by 1s with my X's, which in this case I am. We're going up by 1. That means now I'm going to move on to those Y values and see what's going on there. So we're going to remember subtract the previous term to get our second, or to get our difference. So I'm going to do -4 minus -6. Let me write that out for you. This actually becomes -4 plus 6, which would be 2. Right? Then I do 0 minus -4. We have that double negative again, so this becomes 0 plus 4, which would equal 4. Now I have 6 minus 0, which is 6, and 14 minus 6, which is 8. And you can see we do not have the same number for our common difference here. So that means that we have eliminated the option that this table represents a linear function, but it could still represent a quadratic because we haven't looked at the second difference yet. So now I'm going to do exactly what I just did, but again. So now I'm going to do 4 minus 2, which gives us 2. 6 minus 4, which gives us 2. 8 minus 6, which gives us 2. And this time I do see that I have the same value for my second difference. This means that I have a quadratic function. This one was a little bit trickier, so I'll pause again just to make sure you understand it. And if you're writing this down, you get a good example written down. All right, last but certainly not least, we have an exponential example. Now, an exponential example, that is going to be where we're looking for a common ratio. So let me write that down so we remember common ratio. So this time, instead of subtracting, we are going to divide, which means that I'm going to divide each term by the previous one. So I'm going to do actually here 15 divided by 30, which would give me 0.5. Then I'm going to do 7.5 divided by 15, which would give me, again, 0.5. And I keep doing this. I keep doing the term divided by the previous term. And each time I am getting 0.5. And again, don't be afraid to use your calculator here. That is okay. We have not outlawed that. So once I see that I get the same common ratio for every single set of terms here, that tells me that yes, I do in fact have an exponential function. So 3 cases: common difference, common second difference, and common ratio. All right, so then let's say that I give you a table of values and I say identify the function family that it represents. Here is a suggested step for discovering which function family it's in. Step 1 would be check for a common difference. So that would be just like what I did with that linear function. So see if subtracting works. If subtracting works, then you know you have a linear function. If you don't get the same number when you subtract, then you're going to move on to step 2. And step 2 says, hey, the common difference didn't work. Let's see if the second common difference works. So you'll subtract again. And if that works, then you have a quadratic function. If that does not work, you don't see the same number after the second difference, you'll move on to step 3. And step 3 is kind of starting from scratch. You will erase your work or cross off that work. And instead of subtracting, you will divide and you'll check for a common ratio. And if you do have a common ratio, then that means that you will have an exponential function. Right? So step 1, common difference. Step 2, common second difference. Step 3, common ratio. So let's look at an example. Now here is where I'm going to pause and have you guys try this for yourself. I want to know, is this table of values representing a linear, quadratic, exponential, or non-function? So pause the video now and try it out on your own. All right, by now you've given it a shot, so we are going to go through our solution. Here we go. Again, my x values were counting by 1, so that means I can now look at my y values. Just like before I said, we're going to start with our common difference. So here I go. 3 minus 1 would give me 2. 9 minus 3 would give me 6. 27 minus 9 is going to give me 18. And Miss Carr wasn't ready. 81 minus 27 is going to give me 54. Obviously, those are not the same numbers. So I know immediately that this is not representing a linear function. There was no common difference. Let's try out if the second difference works. So here we go. 6 minus 2 will give me 4. 18 minus 6 will give me 12. And 54 minus 18 will give me 36. Again, I do not have a common difference. These are not the same numbers. So that means the second difference did not work. So I can eliminate the option that it is a quadratic function. Now I am just determining whether or not it is exponential or a non-function, a relation. So I'm going to erase this so I have room. I can tell right off the bat that this is not a non-function because there are no repeating x values. So really, by process of elimination, this must be exponential, but let's prove it. 3 divided by 1 is 3. 9 divided by 3, again, I'm dividing here, is 3. 27 divided by 9 is 3. And 81 divided by 27 is 3. So we do have a common ratio, meaning this must be exponential. If you got that, awesome job. We're going to try one more. Now again, here is where you are going to pause the video and try it out yourselves. All right, by now you have tried it yourself and you are ready to see our solution. Here we go. Again, I'm going to start with that common difference, move on to the second difference, and if that still doesn't work, switch gears to my ratio. So common difference, 2 minus 16 is going to give me negative 14. Negative 2 minus 2 is going to give me negative 4. 4 minus negative 2 is going to give me 6. 20 minus 4 is going to give me 16. And 46 minus 20 is going to give me 26. I notice that these obviously are not the same numbers, so I have eliminated that linear option. We're moving on to the second difference, so I'm going to subtract negative 4. Let me write that out. Negative 4 minus negative 14. This really becomes negative 4 plus 14, which would be 10. 6 minus negative 4, which changes to 6 plus 4, which is 10. Ooh, it seems to be working. Let's see if we get all the way through. 16 minus 6 is 10. Woo. And 26 minus 16 is also 10. Yay! That means that our second difference worked, so this must be a quadratic function. All right, you guys, if you got that great, or if you got that right, awesome job. If you do have any questions, please let your teacher know so that we can help you understand this idea better. Good work today.